So good afternoon, everyone. You're all welcome to CSC 221 class, problem solving in computing. All right, so this is the outline. When we are talking about a problem is any situation or any question or challenge that needs a solution. Now you might be given a task to solve. That is a problem you are being given to solve. Now, when you want to solve problem with computers, you need a systematic approach to be able to identify the problem so that you'll be able to develop a suitable solution for it. Now, in problem solving with computers, we have several steps that are involved. The first step is problem definition. Yes, it's very important to clearly understand and state the problem. If you cannot identify the problem, if you don't know what the problem entails, you cannot begin to solve a problem. So the next step is problem analysis. Now you need to break down the problem into smaller or manageable parts. It's just like, take for example, you have a complex system. You need to break it down to make it reduced to smaller sizes. It will help you to be able to the third step, which is solution logical method to solve the problem. You want to use flowchart or you want to use pseudocode. As you move forward, you'll be able to understand what algorithms are, what flowcharts are, and what pseudocode is. Now, the fourth step is coding, which is the implementation stage. Now you are translating your design solution into a programming language. All right, the fifth step is testing and debugging. Now, when you write a particular program, it's very important for you to run the program to detect errors, which are called bugs, and correct them. You know, while you are coding, you might have made some mistakes. So those mistakes are referred to as bugs. They are the errors. So the fifth level is testing and debugging. You need to test your program and to be able to detect errors or bugs and correct them. We have what we call documentation as the sixth step. Here you write explanation of how your program works so that if anybody picks it up, he or she will be able to understand. They'll be able to get how your program works so that even when they want to carry out a particular step or something associated with it, it will be very easy for them. Then we have the seventh step, which is called maintenance, and that's the last step. Maintenance involves you updating and improving the program when necessary. Just like when you develop a particular website, there will be need for maintenance because there will be a particular point in time when you need to update or improve something on that particular website. So when you are solving problem with computers, maintenance is very, very important. Now, uh, we have the characteristics of a good algorithm. If an algorithm is not having these characteristics, then it will not be classified as a good algorithm. Number one is input. An algorithm has zero or more inputs. That is, it's possible for your algorithm not to have an input. So the second characteristics we have is output. An algorithm produces at least one output. The reason being that you want to solve a particular problem. So you need to know that the solution of your problem must bring out an output, which is the final thing that you're expecting from a particular solution step carried out. So that means your algorithm must produce at least an output. If your algorithm is not producing an output, it's not a good algorithm. Then we also have another characteristics which is called precision. Your steps must be precisely stated and defined. You must be precise, not that it will be cumbered. No. Now we also have another characteristics, and that is effectiveness. Each of your step in problem solving must be basic and executable. If it's not basic and executable, then that means your algorithm is not good enough, because your algorithm is aimed at solving a particular problem. So each of your step must be executable. Each of your step must be feasible, not that you are just including steps that are abstract, that cannot be achieved or executed. Now, we also have another characteristics, and that is finiteness. An algorithm must terminate after a finite number of steps in all test cases. That is why when you are writing an algorithm, it must always terminate. Not that there is a continuous loop that does not have end. Your algorithm must have an end. That is why it has a finite number of steps. Now, take for instance, when we are talking about all these comparison symbols. If you define a particular variable, maybe x, and you say that x is less than or equals to 3, we know that since x is less than or equals to 3, it's a set that starts from any number that is less than 3 and stops at 3. It makes it finite. But when you say, okay, x is greater than 3, it goes on and on to infinity. So, but a good algorithm must be finite. A good algorithm must be finite. All right, moving forward. So, can you see the slide now? Can you see the slide? All right, just give me a moment. Please excuse me.
See what the students are. Sorry, did you touch anything?
It was not.
Or you just use one. You use this one. Maybe I'll remove it so that it doesn't give high score. No problem. You come back. Work it. Yeah, good.
Okay. All right. Sorry about that. So, problem is any situation or question or challenge that needs a solution. So, when you are given a particular task, that is a problem that you have been given and you need to solve it. Now, when you want to solve with computers, you need systematic approach to be able to identify your problem, to be able to develop the solution and implement that solution using a computer program. As we move on, you'll be able to get all this step by step. All right. Now, steps in problem solving with computers. The first step is problem definition. In problem definition, that is the stage where you clearly understand and state the problem. Now, if you have been given a particular task, maybe cleaning a room, that is the problem, cleaning the room. You need to understand what is meant by cleaning the room. So when you understand that problem, you'll be able to identify what are the things that are required, even the items that you need for cleaning. So the second step is problem analysis. You need to break the problem into smaller manageable parts. Just like you want to clean the room, you need to look for the materials you're going to use to clean. So you need to get them ready. You will break them down. Okay, when I want to clean, I need to get broom. I need to get bucket of water. I need to get a mopping stick. Do you understand? You just break it down. So there you determine constraints, assumption, and whatever required operation that is needed. Now the third step is solution design. In solution design, you develop a logical method to solve the problem. This is where you use algorithms. This is where you use flowcharts or you use pseudocode. And the fourth step is coding or implementation. Now, this step is where you translate the designed solution into a programming language. Now, we all know that programming languages, they solve a particular problem or task. So this fourth step, which is coding or implementation, is the point where you translate whatsoever solution you have designed into a programming language. All right, the fifth step is testing and debugging. Now, nobody is above errors. At this stage, you run the program to detect errors. You run it to be able to detect bugs, which are errors, and to correct them. Probably while you were coding, you have meddled with some things. At that stage of testing and debugging, you are able to identify and correct your errors. The sixth step is documentation. This step involves you writing explanations about how the program works for future reference, so that if anybody wants to use your program, they'll be able to know. That is why when one is coding, we usually insert comments. Comments will always give you guidelines like, okay, this is meant for this code, this is what it's talking about, this function, this is what it's talking about. So documentation is very, very important for future reference. The last step is called maintenance. Maintenance, this involves updating and improving the program when necessary. If you build a particular system, there might be a point in time when you need to change some things. Probably you need to update or improve some things. So this step is very, very important, because there are times that you will get feedback, or there are times that you just need to change some things. So this maintenance stage is very, very important. Now, we have algorithm. We use algorithm to analyze a problem. An algorithm is a finite order set of clear instructions used to solve a problem or perform a task. Now, algorithm is a step-by-step instruction. That sequential flow is used to solve a particular problem. And an algorithm, before you can call it a good algorithm, must have the following characteristics. Number one is input. An algorithm has 0 or more inputs. It's possible that your algorithm will not have inputs. Yes, it's very, very, very possible. But now the second characteristics, which is outputs. An algorithm produces at least one output, because your solution must give an end result. So if your algorithm is not producing a final result or a final output, it is not a good algorithm. Now, precision is another characteristic of a good algorithm. These are steps. When your algorithm is precise, that means your steps are clearly defined and stated. It's not that maybe your algorithms are just clustered together or cumbersome. So we also have effectiveness. Each step is basic and executable. Not that you are having steps that cannot be executed, that are not feasible. It's just like now they ask you to write a particular business plan, and they're asking you for the financial projection of your business, a startup business, a new business in the next 2 months, and you're writing, in the next 2 months, my business should have produced like around 2.3 trillion naira profits. It's not feasible. So when you are writing an algorithm, each of the steps must be basic and executable. It must be feasible. Then we have finiteness. An algorithm must terminate after a finite number of steps. Your algorithm should not be one that does not end. When you're talking about termination, you are saying that it has an end. If your algorithm does not have an end and is a continuous loop that does not end, then it is not a good algorithm. Then also your algorithm must be clear and unambiguous. Each of its steps should be clear. It should provide understanding and must lead to only one meaning, not that it will now lead to several meanings, which can cause confusion. Now, your algorithm also must be language independent. Your algorithm must be able to be executed or implemented by any programming language. Not that maybe your algorithm is now strict or maybe confined to a particular programming language. No. When we are talking about independence, that means that thing can do without another thing. So your algorithm must be language independent. It must not depend on a particular language. It must not follow a particular programming language syntax. So your algorithm must be in plain instructions that can be carried out or implemented in any language. I hope we are together and we are getting. All right. Now we have a typical example of an algorithm. Typical example of an algorithm. So now, the first example is an algorithm for preparing hot beverage. Now, step one, boil water. You know, when you want to prepare an hot beverage, you need hot water. So you boil water. Then step two, you add tea or coffee to a cup. It depends on the beverage you want to prepare. Then number three is you pour boiled water. You pour it on it. Maybe let's assume you want to prepare Lipton. After boiling the water, you put the Lipton in the cup. You know you're going to pour the boiled water in it. Then you can stir. You can add sugar. You can add milk or whatever you want to add to it. Then the final stage, which is the final step, you serve. Not that okay, you just leave the boiling water there. And these steps, they can be understood even if someone picks this up. It's just like, there are times that probably you don't have an understanding of something. You go to YouTube for tutorials. Now they give us step-by-step guidelines. If those guidelines are not understandable, they won't be able to communicate their mind to you. So also is algorithm. Algorithm, the steps must be in plain language that is understandable. Now, when you see this, someone can just say that he or she wants to prepare hot beverage, and he sees that the person will boil water. We had the beverage, whether tea, coffee, or whatever it is, to a cup. Then pour the boiled water, stir it, add sugar or milk or whatever, depends on your preference. Then serve. The person will be able to attain it. So algorithm must be able to solve that problem that you intend. Then this is another example, which is a mathematical example. It's an algorithm for finding the sum of two numbers. Then the first step, you start. Since we are adding two numbers, you input the two numbers. Let's assume we denote them using variables a and b. So you input two numbers a and b. Then you compute the sum, which is a plus b. Then the first step, you display the sum. Then the fifth step, you stop. So that's it. That's what we call termination. There must be an end. Now look at display sum. That's an output. Display sum is an output. So your algorithm must have an output. Input two numbers a and b. Those ones are the inputs. So if you look at this example and you take it side by side with the characteristics of a good algorithm, you will see that it is able to fit in perfectly. All right, moving forward, we have flowcharts. A flowchart is a graphical representation of an algorithm using standard symbols to illustrate the sequence of operations and decision points. You know, we humans, we are audiovisual. We learn by what we see, what we hear. Now, for the visual aspects, after writing algorithms, we can translate them into a pictorial or graphical representation, and that is what we mean by flowchart. Now, when you want to use flowchart, there are standard symbols. It's not that you just draw flowchart like a cartoon where you will draw a head as circle, you now put two eyes, you put nose, you put mouth. No, we have standard symbols. That is why it is a graphical representation of an algorithm. Once you're able to develop an algorithm, it's not difficult for you to develop a flowchart. All you need to do is just to translate your algorithm step by step using the standard symbols into a flowchart, and you have a flowchart. Now, flowcharts are made of boxes, diamonds, and other shapes connected by arrows, which signify the flow of the process. It enhances clarity of program logic and facilitates error detection. While you are drawing your flow chart, you can detect errors that, okay, this is not supposed to be here, this is not meant to be, then you correct them. All right, so these are common flowchart symbols and their function. We have a lot, but these are very, very common. Now, the first symbol is oval. An oval represents the start or end of a process. Ovals are used to begin a flowchart and to also terminate it. You know, we say flowchart is a graphical representation of an algorithm. So in as much as flowchart is representing an algorithm, that means a flowchart also must be finite. It must terminate. It must have an end. So once it's beginning, you always have to start a process. You need to terminate. And the symbol used to achieve that is oval, and the symbol is indicated there. Now we also have rectangle. Rectangle denotes a process or operation step. Like take for instance now, if you want to add two numbers, while you are adding, addition is a process. So it is denoted using rectangle. These are standard symbols. Now we have arrow. The arrow indicates the flow between steps involved in a particular flowchart. Now, okay, when you start, you move to maybe taking an input. So it's the arrow that will connect them. And the arrow can either be to the right, to the left. It depends on the particular point of your flow. Now we also have diamond. Some call it rhombus. So if you see rhombus somewhere, don't think maybe it's wrong. It's either diamond or rhombus. So making symbol. Like now, maybe you want to compare two numbers. Okay, maybe you want to compare A and B. You are asking, is A greater than B? You know, if A is greater than B, there will be a step to take. If A is not greater than B, there will be another step to take. So in situations like that, you use the decision-making symbol, which is diamond or rhombus. Now we have another symbol which is called parallelogram. This parallelogram is used for input and output operation. Now, whenever you want to take in an input, you use the parallelogram to signify that. When you want to represent an output, you use the parallelogram. So parallelogram is used for both input and output operations. All right. This is an example of flowchart. Now, this flowchart is calculating the sum of all odd numbers between 1 and 100. Now, if you want to develop a flowchart, you would have developed an algorithm. So, and now, this is talking about calculating the sum of all odd numbers between 1 and 100. This is a problem. You need to understand this problem. What are odd numbers? You know, odd numbers, they are not divisible by 2. So odd numbers start from 1. Odd number 1, we have 3, we have 5, we have 7, we have 9, we have 11, and all. There is a pattern. Before you get the next odd number, you have to add 2 to a preceding odd number. Are we together? So now, when you want to develop a particular algorithm for that, you need to analyze it that, okay, there will be a number, a startup number, since it's between 1 and 100, the startup number will be 1. That 1, you add 2 to it. When you add 2 to it, there will be an update. The result of the addition, you will add 2 again because it has a definite pattern. So you've known that. So that means when you start, you use hover to represent the start. You initialize your sum. You say sum should be 0 because we are adding continuously. Then n is 1. That's the first number. So now that is having a parallelogram. Reason being that it's an input. You are saying that your sum is 0 and your n is 1. Now you move to sum is equals to sum plus n. Your sum is 0. You've initialized it to 0. And the first number is 1. That is 0 plus 1. It's a repetitive addition for this odd number. Now it's a rectangle because it's a process, addition process. After you have added that and the sum is is now sum plus n. Now your n will be updated because we are looking for odd numbers. So your n will be updated as n plus 2. That is also a process. Now you continue down, then you know your n will keep increasing. Now you get to a point where you need to make a decision, where your system needs to make a decision. It will ask, is n less than 100? The reason being that 100 is an even number, not an odd number. So the last number must not be 100. So it will ask, is n less than 100? You have been adding 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. O n is less than 100. Because the last number, that would be 99, which is an odd number. So if it is yes, look at the direction of the arrow for yes. If it is yes, because you know it will keep adding, it will repeat that step of adding that number to sum. Now, if it is not less than 100, then it will move down and display the sum. That means it's true. As time goes on, when you start learning about all these conditions, if, else, and all loops, all these while, do, and all, there is always a particular criteria to meet before it terminates. So once it's able to display the sum is an output. So it is in parallelogram shape. Then it moves to stop. It must terminate, and that is over. I hope we are together and we get that. All right. Now we have what we call pseudocode. Pseudocode is an informal human readable representation of code. Now in pseudocode, you combine natural language and elements of programming language. But you know pseudo, when we are talking literally about pseudo, we mean false. That is, this is not a code. It's not a programming language. You are not coding. It's a pseudocode. It's a false code. It's not really a code. So this pseudocode is used to define what is to be done in a program. It's just like a semi-coding. It's not really a programming language that you are coding. It's something you have written in formal language that you understand, in plain language that you understand. It's not following a strict syntax of any programming language. It's like what helps you to be able to translate an algorithm or flowchart into any programming language. So that means this pseudocode simplifies complex problem-solving steps, and it makes algorithms easy to understand and review. All right, example of pseudocode. We want to write a pseudocode for area of a square. And we know that area of a square, because square has all of its sides to be equal, is length times length, any of the lengths. If you have a square to be having a length of 2, that means all of them are having 2, 2, 2, 2, 2, 2. So area of a square is L times L, or L square, length times length. Now, pseudocode, we say, okay, start. Input the length. Then it will divide the area as length times length. You know, that operator is multiplication operator, that asterisk. Now, you know that asterisk is a standard operator that we use for multiplication in programming. Now look at the way this pseudocode has been written. You'll discover that input length, area is equal to length times length, output area. They're not starting on the same line with start. We are saying that, okay, when you start, these are what you do. You know, it's so close to programming languages, how you write programming languages, how you code. But it's not the actual code. Anybody can just take this and understand and translate it into any programming language. Do you understand? You can use any programming language to implement this. So pseudocode is not an exact programming language. It's not that you have really coded. It's just like you have translated your algorithm further. So that is why it is called pseudocode. Now, before we move on, so I'll be calling out the attendance code 1. So the attendance code 1 listen attentively, please, is Q9 YV3. Let me call it again. Attendance code 1, Q9 YV3. Is that duly noted? Is that duly noted? The attendance code 1 is Q9YV3. All right, let's move forward. Now, modeling. When we are talking about a model is a simple representation of a real world. It's like you are abstracting a whole system. Now, it is used to describe, explain, analyze, or predict how something works without dealing with all its complexity. Take, for instance, your body system. You have several systems in your body. You have the respiratory system, you have the nervous system, you have the digestive system, and others. You can decide that, okay, you want to model a particular system, which is the respiratory system. Then you can start talking about maybe the elements in it, maybe the lungs, maybe the diaphragm. Now, you're not talking about the whole body because the whole body is complex. Now you decide that, okay, you are picking a particular part of the system of the body and you are trying to use it to explain how the body is. So when we are talking about model, it's a simplified representation of a real world. Just like now, when let's assume you are given a particular project, like maybe you're a final year student and you're given a particular project, and you have to design and implement. Now, when you want to design and implement, you maybe they ask you to carry out a project that concerns um, maybe road, especially traffic system. Now, you will not just go to maybe a particular junction and you just look for a light and just put there and just be controlling traffic. No, there will be some hazard, there will be some mistakes. So you need a particular representation, a prototype, something that will just be an abstraction of that system. That is why after that, if what you have experimented, what you have simulated after modeling is okay, you can now do a full implementation to carry a larger scope. So when you're talking about a model, it captures only the essential aspects of a particular problem and ignores unnecessarily details. It's a way to translate real world complexity into a structured form. So models are very, very important. Like now, we all know toy cars. Now you want to build a car, you can just give a prototype, a model, something small. You just build it. Okay, you put the mirror, okay, you put the steering, you put the dashboard, you put the seat, you design it, then you bring it out. That is you modeling a car. You are giving a prototype. So if there are any changes you want to make, it will be cost effective to make the changes. But if you have built a car, let's assume now you have built a car already, maybe Toyota Corolla, and you discover that there is an issue with the plug, the way it is not okay, it will cost you a lot for you to correct it. Or maybe you want to maybe uh, look for a way to reduce the waiting hours of people in an hospital. You now go and tell them in the hospital, you need to employ 10 staffs, 10 doctors. You ought to have carried out a particular modeling such that you look at the inflow and outflow of people in the hospital. You look at how the crowds are. You look at the waiting time of people. You just oppose them before you take decision, because at the end of the day they will be redundant if they are too much, and if they are not sufficient, they will not be able to solve the problem, the waiting time problem. So modeling is very, very important. Now we have different types of model. Now, we have the physical model. When we are talking about physical model is a real, tangible representation of an object. You know, when I was talking about a prototype of a car, that is a physical model. Now, we also have what we call mathematical model. Every mathematical equation is a model. Yes, is a model. So mathematical model uses equations and formulas to represent a system. They are used for analysis, they are used for prediction. You can decide that, okay, you want to know the distance from here to maybe Ilesha. You can employ different mathematical formulas because you are trying to look for something that can represent the distance from here to Ilesha. So when you are using those formulas, you are employing the use of mathematical models. All right, now we also have what we call conceptual model. They show ideas, they show relationship. They are used for planning and explanation. And an example is flowcharts. We also have block diagrams. Like now, as time goes on, when you start embarking on project and start writing maybe report, you will discover that there are times when you want to represent a particular idea or you want to represent a particular relationship, you have to show some concept diagrams. One of them is block diagram. You show them that, okay, this flows from this to this. This is based on this particular idea, this process. So you use conceptual model. Now we also have what we call logical model. They represent systems using rules and logic. They are used in decision making and program. And examples are decision trees, truth tables. Even if you don't know decision trees, I know you're conversant with truth table. Now, they are all logical model because when something is logical, you know, it can be either true or false. That is why when we're talking about the decision making process using that what's the name? That symbol, rhombus or diamond, you'll see that there was an arrow that leads to yes and there was another arrow that leads to no. So logical model, they use rules, they represent system using rules and logic. So when we are talking about logic, we're talking about maybe true or false. All right. So moving forward, we have several reasons for modeling. It simplifies complex system. You know, I made an example of a whole body system being complex. You can decide to model using the systems of the body, maybe the respiratory or the digestive or whichever one. It aids understanding and analysis. You'll be able to interact with it. You'll be able to speak to it. Not that you're not just you know when we're talking about how we solve problem, you need to break it down. If you don't break it down, you'll be able to easily have the solution because it will be so cumbersome for you, and at the end of the day, you will give up even before starting. So that is why, you know, they always say that if you don't know where to start start from the beginning. So when you are modeling, it aids understanding and analysis. It also improves your system design because whenever you want to make changes, you can make changes without stress. You can make changes without incurring costs. It's not that maybe you've done something on a large scale and you need to go and get something else. Maybe you have pre-ordered something, and that's why you know we have modeling softwares. We have softwares that you can use to model so that you will not run at loss. Yes, so it saves time and cost, just as I've said earlier. Also, it enhances communication. You know, I said you'll be able to speak to it, you'll be able to interact with it. It supports decision making. When you see how it behaves, if it's not giving you the output that you desire, you can now decide, okay, let me change this. Let me attend to this. Do you understand? All right. So it predicts system behavior. That's why modeling is very, very important. You know, you have a particular output in mind. So it helps you to make known the system behavior, how the system will eventually behave if you carry those steps that you have planned to carry. It enables